Hi guys, hope you guys had a great spring break and we're coming back in starting the new unit. You should have been working on your quiz for 5.2, which was on the sinusoids on Wednesday of this week. And you should have completed the parent graphs for the other trig functions, tangent, cotangent, secant, and cosecant on Monday. So that kind of wraps up the chapter 5 that we were doing. So we're getting ready to jump into a new unit. And like I said in my earlier videos on what we're trying to do for this year, we're basically doing things that are going to be useful in solving equations. And so we're going to do a little bit of review here today, but also talk a little bit about the importance of notation and communication and how we're going to work through simplifying using identities. Now, before we can get to simplifying, we do need to kind of talk about what are identities and what's important about them. And we're going to identify some basic ones that you should already know, but that you definitely want to put in your memorization folder of things that you should know going on to calculus next year. Now, just to remind you, there are many types of mathematical equations. Several we've already encountered this year. So we haven't maybe not have called them this, but this is what they are. So name equations are equations that give a name to a specific expression, where we're just naming the function f of x, and then we give a rule or a formula for how to calculate the output of the function f of x using this formula by plugging a value in for x. So you have an input x, an output y, and the name of the function is f. So that's a name equation, just gives it a title. Conditional equations are things that are meant to be solved. And so basically, they're only true for a finite number of values. That's why we're looking for a solution set. So for example, here we have x squared minus 6x plus 8 equal to 0. And so taking a look at that, what we could do then is say, well, let's factor it, obviously. So we could do x and minus 2, x minus 4 equal to 0. So your solution set for this one, we go straight to it, is going to be 2 and 4. There are only two values of x, which make this conditional equation true. Now, a contradiction is an equation that actually equates expressions that are never equal to each other. 5 never equals 7. Or in this case, a square root of -1 minus x is never equal to the ln of x. In other words, there's no intersection point for these two graphs. If I were to graph a transformed square root and the log graph, they would not be the same. So for example, if we just go over, I already put this in Desmos. And so you can see here that we have our function that is right here. The red graph is going to be the square root function. We had a flip and it shifted to the left. And then we had a natural log function, which we hopefully remember from our unit earlier in the year. And we can see that they're not going to intersect each other ever. So there is no solution to this equation. So the solution set, our solution set up here was 2, 4, but our solution set down here is going to be the empty set. There are no values that make them true. We could also use null set appropriately for that. All right, now taking a look at our identities, what's important about identities? Now, for those, they're still equations, and they look like equations, but they're going to equate two expressions that are true for all values in the domain of both expressions. So, for example, when we've seen this in Algebra 2 before, we were talking about the big idea that the square root of x squared is equal to the absolute value of x. This is true for all x. The domain of these two functions is negative infinity to infinity. So this is true for all values in the domain of both expressions. We've also seen this like when we do rational functions. So if I had something like x plus 1 over x plus 1 times x minus 1, that is equivalent to 1 over x minus 1, but only on the values in the domain of both expressions. And we know from over here, remember that this is not defined when x is plus or minus 1. So our domain of this equation is going to be all x such that x does not equal plus or minus 1. These two values would return the exact same real number for every value of x, except in the case of where x is 1 or negative 1. We used to see this when we wrote our exceptions. We would say that this is equivalent, your original is equivalent to 1 over x minus 1, except when x equals negative 1, the factor that we canceled out. Technically, it is this idea that they are the same when x is 1 because they're both just undefined. But when x is negative 1, the original is undefined, but the simplified version is defined, and so that's why we had to put the exception in. But in general, we could say that this is true on its domain for the equation, and so we could take care of that. So identities are important because they're two equated expressions that serve as synonyms of each other. And so what that means, and the big idea here is they can be substituted without loss of generality. But the whole point of having identities is that we can use them as substitutions to help us do things like simplify or transform equations into things that are easier for us to work with. Now, we've had several of them in Algebra 2, things that had to do with factoring. I mean, I obviously, when I did this up here, I actually very trickily used an identity to go from x squared minus 6x plus 8 to its equivalent form, x minus 2, x minus 4. Those two expressions are equal for all values of x. And so I made a substitution in my solving because they are equal to each other. And that's what an identity is. So when we're looking at trig identities, those are things that involve trig expressions. And so now we're just kind of moving into non-algebraic type identities that we would have seen. Now we've already seen these this year, and the ones that we're going to start with here are going to be our reciprocal identities. So the first four right here are actually all of these are your reciprocal identities. That sine and cosecant are reciprocals of each other, cosecant and sine are reciprocals, and so on. Now, we did see that when we did the right triangle trig. If you will remember, if you had theta, this was opposite, this was adjacent, and this was our hypotenuse, right? And so when we were talking about, say, for example, sine of theta, sine was, I don't know, I totally wrote that down wrong, and I'm sure somebody's yelling at me in the video. That's opposite, and this is adjacent. So sine is opposite over hypotenuse. Cosecant of theta is hypotenuse over opposite, and you'll notice that they are reciprocals of each other. And so it's this idea that what we have are these relationships between trig functions that we want to know and that we do want to memorize. And this 1 over just means reciprocal. Now, let's talk about a proof, because obviously, you know, this over here is me just kind of explaining it with the right triangles, but we do want to remember and explain this using our terminal point definition and kind of give ourselves a basis of why this works and prove it for all theta, not just the theta and the right triangles, which is what I showed kind of a little mini proof over here on the side. So let's say that we're given, okay, just to kind of go back to, in proofs in geometry, you had to be, what were you given? So we're given that if we have a terminal point, right, and that terminal point can be anywhere, x, y, for some angle theta. And that the terminal point definitions were that, say, for example, sine of theta was x, not x, sine of theta was y over r, cosine of theta, x over r, tangent of theta was opposite, which is y over x, Your cosecant of theta is r over y. Secant of theta is r over x, and cotangent of theta was x over y. So this is all given information from prior sections that we had. So a lot of times, you don't always have to write the given down. I'm just kind of including it here for you guys to remember that we do have that. So one of the things that they've asked here is to basically do a proof. To write a proof, and I'm just going to get that out of the way, that the tangent of theta equals 1 over cotangent theta. Now, the type of proof that we like to do when we are doing these types of trig proofs are going to be what are called transitive proofs. And these transitive proofs have a very strict format when you take a look at it. You want to make sure that you are doing your pick a side, 1 equal. We don't know this is equal. If we're trying to prove this, maybe I should put a little question mark above it. I want to know if this is true or not. Now, from our knowledge, we know that it's true. We've worked with this, but we're going to prove it using a transitive proof and using the definitions of the trig functions in terms of x, y, and r. So the first step in a transitive proof is usually pick the more complicated side of this possible identity that we're trying to prove. So I'm going to pick 1 over cotangent theta because I think a fraction is more complicated. Then you start your identity proof by starting to do a substitution. It said use the definitions of the trig functions in terms of x, y, and r. So 1 over cotangent of theta would become, and I'm going to use this identity right here, cotangent of theta is x over y, and I'm going to substitute in x over y. Now, typically, what we do at that point is we get it in those terms. We maybe do a little algebra. Anything that is an algebraically acceptable way of simplifying from algebra 2 is okay. And we know that dividing by a fraction is the same as multiplying by the reciprocal. So it becomes y over x, which is simply y over x. And then at that point, we can look back up here to our given, and we can now use the identity that y over x is tangent, and we can substitute that in. So this becomes tangent of theta. And do you see how we have our right-hand side of our equation? We have a string of equals. This is the transitive part. And then we have our left-hand side of the equation. And the rule is that from each step as you move along in your proof, that what you are allowed to do is a given identity substitution or legal algebra. Those are the things that you are allowed to do to prove it. Now notice that I went across on the paper there. Some people do like to, instead of going across, they like to go down when they do this. So let me show it over here on the side, simply as a proof going down. So I would do 1 over cotangent theta, 1 over x over y, and then I go down, y over x equals tangent of theta. So you see it still has that right-hand side, equals, equals, and then the left-hand side over here. And that's what we call transitive format. And so we get to conclude at the end, therefore, 1 over cotangent theta equals tangent theta. All right, so, and we could do that for all of them. I'm not going to prove each of them, but I just wanted to prove it for one to show you what that looks like. Okay, so I'm going to stop this video at this point because I think that gives you a little bit to think about. You may want to go on your own paper and go ahead and prove maybe 2 more. So why don't you try on your own paper? Let's have you guys do secant theta equals 1 over cosine theta. Prove that, and that's 1. And 2, have you guys try maybe cosecant theta equals 1 over sine theta. So do the little 2 mini proofs for that, and then come back to the second part of the video for these notes.